Let's take a look at example 2 from section 13.9. In this example, suppose we have a manufacturer that wants to determine the profit P in dollars obtained by producing and selling X units of a product 1 and Y units of a product 2, where the profit is given by the following equation. The profit P of X is a function of X and Y is equal to 8X minus 10Y minus 0.001 times the quantity X squared plus X times Y plus Y squared minus 10,000. We want to find the production level that's going to produce the maximum profit. So we want to find out how many units of product 1 and how many units of product 2 to make, as well as they also ask us what is the maximum profit that would be made from that production level. So the first thing we're going to do, start off as we've done in the past, we want to begin by finding our critical points. So we need the partial with respect to x and the partial with respect to y of the function p. If I take the partial with respect to x, then I'm thinking of y as a constant. This should give us an 8. This term here, with respect to x as a constant, this derivative would be 0. I have this constant multiple, which will stay there. And then the derivative of x squared plus xy plus y squared with respect to x would give us 2x plus y. So this is our p of x function. We now want to go through and differentiate, find the partial of p with respect to y. This term would be 0 because with respect to y, x is a constant. The derivative of negative 10y would be negative 10. And actually, I'm sorry, this is a typo. This should be, in the notes should be positive 10. Should be a positive 10 here. Minus, with respect to y, this term would be 0. The derivative of xy is x, and the derivative of y squared would be 2y. And that constant at the end, the negative 10,000, its derivative would be 0. So the partial of p with respect to y would be this equation right here. 10 minus 0.001 times the quantity x plus 2y. We're now going to go ahead and find our critical points. For the critical points here, we want to solve for where p of x is equal to 0 and simultaneously p of y is equal to 0. So we need to figure out where is the partial with respect to x of p and the partial with respect to y of p equal to 0. There will be no other critical points possible. The partial with respect to x and the partial with respect to y are both polynomials, so there's not going to be any places where either one of those two partials would be undefined, which we know is a second potential source of critical points. I take each of our expressions for the two partials, I set them equal to 0. For this first equation, one of the things I can do is I can take the negative 8 to the other side, I can subtract 8 to both sides, and then divide by the negative 0.001, and that will leave us with 2x plus y will be equal to 8,000. If I look at the partial of p with respect to y, we can do something very similar. I can first subtract 10 from both sides, then divide by negative 0.001, and that will give us x plus 2y equals 10,000. So when looking for these critical points, it boils down to solving this system of equations. We need to find the values of x and y for which 2x plus y is equal to 8,000 and also for which x plus 2y equals to 10,000. I didn't show this kind of work in the last example that I did, so let me just kind of work through some of the details for this one. In order to solve the system, you can use any method you might have learned in a previous class. You can do the substitution method, would work great. I'm going to use the addition method where I want to create equal but opposite coefficients, and I'm going to choose to focus on getting rid of the x variable. I can multiply the second row, or that second equation, by negative 2. That would produce negative 2x minus 4y equals negative 20,000. And then in the numerator, or in the first part, we have the 2x plus y equals to 8,000. Because the x terms have equal but opposite coefficients, I can add those two equations together, and the x terms will cancel. That will leave us with y plus negative 4y, which is negative 3y, equals 8,000 plus negative 20,000 would be negative 12,000. And then we can get the y by itself by simply dividing both sides by negative 3, and we would get that y is equal to 4,000. Once you have the value for y, you can go back and plug it into either one of the other two original equations to solve for x. I'll substitute it back into the 2x plus y equals 8,000 from our system. Wherever I see a y, I can put 4,000. So we get 2x plus 4,000 equals to 8,000. Subtract 4,000 and divide by 2, and we would find that x equals to 2,000. So we do have a critical point here. It's x is 2,000 and y is 4,000. The next thing we would want to do is to use the second partials test to see whether this point would produce a minimum, maximum, or perhaps neither. Could even be a saddle point. So we need the second partial of p with respect to x. If I take this first partial differential, this first partial derivative here, and if I differentiate with respect to x again, the derivative of 8 will be 0. We have a constant multiple of that negative 0.01 term, and the derivative of 2x plus y with respect to x would be just 2. So the second partial of p with respect to x ends up just being the constant negative 0.001 times 2, which gives us negative 0.002. Similarly, if we come up here and we find the second partial of p with respect to y, the derivative of 10 is 0. I have that constant multiple of negative 0.001, which is there, and the derivative of x plus 2y with respect to y is going to be 2. So we get 2 times the negative 0.001. So the partial with respect to y is also going to be negative 0.002. We would also need the second partial of p with respect to x and then y. That would be simply a matter of going back to this partial right here. Take the partial of p with respect to x and take its partial derivative with respect to y. The 8 would be 0. We have that factor again. And then with respect to y, the derivative of 2x plus y would just be 1. So the mixed partial pxy works out to be just negative 0.001. And now we're set up for our partials test. The second partials test means we need to evaluate the expression for d, which is the second partial of p with respect to x, evaluated at the critical point, times the second partial of p with respect to y, evaluated at the critical point, and then subtracting the mixed partial, evaluated at the critical point, squared. Luckily for us, it's a pretty easy evaluation because all three of those partial derivatives ended up being constant functions. So the value for d is going to be negative 0.002 times negative 0.002, subtracting negative 0.001 squared. If you work this out, we get a d value of about 0.000003, which in particular, we don't care about the value, we just want to know the sign of it. D happens to be positive, it's greater than 0. In addition to d being greater than 0, if we check the sign of our second partial with respect to x, that was the negative 0.002 value, which was less than 0. If d is greater than 0, and p, the second partial with respect to x, is less than 0, then that means that that critical point is going to produce a maximum. So the production levels we would want to use in order to create the maximum revenue or maximum profit here would be we would want to create 2,000 units of type 1 and 4,000 units of type 2. So that answers the question of the production levels. They also asked us what was the maximum profit as a result of this. You would just go ahead and plug these values into the profit function. Everywhere I see an x, put 2,000. Everywhere we see a y, we would put 4,000. And I'll leave that computation up to you. If you substitute in the order pair 2,000, 4,000, we should get a maximum total profit of $18,000